Welcome you all. We are now in this course Fundamentals of Compressible Flow, Module 2. So, in the first module we discussed about the fundamental aspects of fluid mechanics and gas dynamics that are used to be covered in undergraduate syllabus. Now, at higher level in this compressible flow, we will make use of those equations, those properties and try to study the fundamental behavior for the flows that are compressible in nature. So, this is the first lecture on the module 1 and this title of this module is wave propagation in the compressible medium. At the end of the lecture, we will come to know about some brief introduction to compressible flow and we will talk about some important parameters that are used specifically for compressible flow such as speed of sound, Mach number, and we also talk about wave propagation in the compressible medium, means that under what circumstances we say the fluid can be treated to be compressible in nature. Now, to address the fluid flow problems, we will develop some fundamental flow equations that are routinely used for the flows that are compressible in nature. Something about isentropic flow which is also equally important, because these isentropic flows are taken as the reference or basics for subsequent analysis. Now, we will start this lecture. Now, we will revisit something what we discussed in the types of fluid flow, that is incompressible and compressible flow. Just to give some brief insight or revisit those concepts, I will just spell out some of the important aspects. So, when the fluid is moving at low velocities, the variation in the pressure is usually small enough to justify the behavior of incompressible flow. That means, to decide whether the flow to be compressible or incompressible, the pressure as well as velocities is important, and for incompressible flow these pressure changes are very small. Since the density does not change in the incompressible flow, the energy equations can be decoupled so that continuity and momentum equations are solved for pressure and velocity. Now, to address this flow phenomena, we normally encounter three major equations: continuity equations, momentum equations and energy equations. When the fluid is incompressible nature and where density is a invariant quantity, so it does not come as a specific parameter for calculation through these equations. So, in normal circumstances, the mass or continuity equation and momentum equations are solved simultaneously for velocity and pressure, and for to calculate the thermal energies or other types of energies or internal energy of the system, we have to use the equation for energy equations explicitly or separately. But this is what we do in the incompressible flow. Now, when you look at the compressible flow, what we see is that at higher velocities the variation in the density as well as temperature to the pressure changes is large. So, in that aspects, in terms of addressing those parameters, we have to take two more other equations, that is known as, in addition to continuity, momentum and energy, we have to bring into two more equations, that is equation of state and the entropy equations, and that is specifically used when there is a directionality in the flow. Hence, the compressible flows are routinely called as variable density flows. The very bottom line in this study is that for compressible flow we need the density changes to be a significant parameter. Just to give some brief insight, we say liquids are incompressible, and in our case in a commonly used situations we say water, whereas gases are compressible nature, and in our normal circumstances air is the is one of the fundamental gas. So, just to give a number, one can say that air is about 20,000 times more compressible than water. So, this is how it makes the distinction between a compressible flow and incompressible flow. Now, we will not deal about incompressible flow now onwards, we will specifically talk about compressible flows. Now, to address this compressible flow, the first fundamental parameter we are going to look at is known as compressibility. So, what it does is, so it is given by this expression kappa. What it says is that it says the variation of density with respect to pressure. So, this is what the differential term which is used here, variation of density with respect to pressure, and this density change is taken as as one of the parameter, and with respect to its original density rho, how this parameter changes. So, this is the fundamental definition of the compressibility term mathematically. Now, let us use these equations logically for the flows to occur. So, as we say that since our situation is such that we only use this the gases as the compressible gases as a compressible medium. So, the very bottom line is that we can use the ideal gas or equation of state for the gas. So, if you say this equation of state, we write P is equal to rho R T. So, the pressure, density and temperature are related with a characteristics parameter R. Now, looking at these equations, if we want to see that how the pressure changes with respect to density, then one must say that what happens to temperatures. So, obviously, so while looking at this equation, differential equations, and we want to make any changes in the density, then we must do something about temperatures. So, this brings thermodynamics into picture, under what circumstances I can change the density with respect to pressure. So, for that reasons, one assumption, thermodynamic sense in one assumption says that I can hold temperature is constant. So, this is what the kappa T is represented as compressibility at constant temperature. So, these differential equations now becomes to ordinary differential equation, now turns to a partial differential equation, where this kappa T is looked at the density change at constant temperature or for isothermal process. But having said this, so we call this as a isothermal compressibility. But having said this, but important issue is that it is very difficult to change the density, although it is mathematically feasible or thermodynamically feasible, but it is very difficult to change the density with respect to pressure by while maintaining temperatures to be constants. So, for that reason, another way of looking at changing this compressibility is defining a term called as isentropic compressibility, kappa S. So, here what the thermodynamic assumption says that instead of temperature you keep entropy to be constant. So, so that is what it gives an indication that one can think of an isentropic process where the compressibility parameter can be addressed, or in general density can change with respect to pressure while maintaining entropy to be constant. So, this basic definition tells us that the how density can change with respect to pressures. Now, moving further, let us see that how density change with respect to pressure is addressed through isentropic process. So, for this reason, let us consider the situation of what we call as wave propagation in one dimensional mediums. So, to bring out the simplicity, we talk about a one dimensional medium. So, for this one dimensional medium, the first thing what you see thermodynamically, that we have a cylinder and enclosed in a, we have a cylinder in which a piston is enclosed. So, the entire idea is that it is a the top part and bottom part or bottom wall of the cylinder we have. One side face we have the piston, while the bottom surface of the cylinder is you think it to be a empty. So, that there is no wall, physical wall. So, ideally what we can see that this can be thought of consisting of a gaseous medium, where lot of gas molecules we can find on either side of the piston, which is and in the cylinder. So, statically, so in this situation we can say that gas is hypothetically at rest and piston is in equilibrium. So, now what you do is that in the next instant you give a little bit of push to the piston. Now, when you give this, when you give a push to this piston, what is going to happen? These gases on the downstream side of the piston gets affected. So, as if what we feel is that at the first instance we say that the first layer of gases they gets affected, subsequently they transfer the information about the movement of the pistons toward this next layer, subsequently this information keeps propagating to the downstreams. So, eventually what happens, the gas molecules which are just adjacent side of the piston gets disturbed, and that disturbs the next layer of the gases. So, why it happens? To theoretically model this, what we say is that we say there is a wave gets created, and in the first instance we say let this wave be a compression wave. So, this compression wave keeps moving into in the stationary medium. So, when it moves, so what you see is that behind this wave whatever gases are there, now they have make their changes because they got the information about the piston movement, and but as long as the wave does not pass through the stationary gas, that is other side of the piston. So, they do not know about the motion of this wave. That means, the information or changes that happens through this moving wave, we can differentiate this the entire stationary gas now as a moving gas, other is stationary gas. So, moving gas I mean the piston, the way the amount of the velocity which is given to the piston, with same velocity the gases they try to move, while the other side of the moving wave will this all the gases they are stationary. So, this is the philosophy how it works or how the information gets propagated through this movement of the piston. So, now in the beginning we say that this is a moving wave. Now, hypothetically you say that had this moving wave be a weakest disturbance. So, weakest disturbance means this disturbance is very small, and this, so since we say it is beginning we say it is a compression wave, so obviously it is the pressure parameter that is going to be concerned. So, if this wave or the pressure pulse is happens to be very small, then this wave we call this as a, this moving wave we call this as a sound wave, or in other words we can say the sound wave is the weakest pressure disturbance. So, it travels always in the medium. Whenever we talk, disturbance is created, it moves at speed of sound. Now, this is what we see, that movement of the sound wave in a gaseous medium. Even one can create a sound wave when the medium is liquid, we can have a sound wave when the medium is as well solid. That means, sound wave can travel in any medium, that is gas, liquid or solid, but it does not exist in the vacuum. So, it requires a medium to travel. That is the reason in outer space we do not have a sound waves, because there is no medium as such. Now, when you actually see the, when this weakest pressure moves at the speed of sound, we can also quantify the what is its speed. So, in down the line we will derive this expression, but for the sake of these things, sake of continuity, I can say and estimate for a typical conditions the speed of sound in air is about 340 meter per second, and that speed of sound in water, this is about 1480 meter per second. That means, speed of sound is higher in liquids. Now, had this situation be a incompressible situation, the pressure disturbances would have felt at every locations at same time. So, there is no question of sound waves. Okay. Now, we will bring about some mathematical orientation whatever I have explained through a analysis called moving gas analysis and stationary gas analysis, and this falls under the domain that we are looking at a one dimensional medium. So, what we see is that, so the first instance when we talk about the moving gas analysis, we say that there is a moving wave, it is moving at certain velocity. Now, how does moving waves gets generated? So, we give a small piston movement, that means piston is given a velocity dv. So, when this piston is given a velocity dv, the gases in one side of the piston, they move at velocity of, also velocity of dv, and because of this is a moving gas, this moves at speed of sound a. So, this moving wave or I can directly say it is a sound wave. So, it moves with a velocity a. Now, let us see that on this side we have stationary gas or stagnant gas, and this side we have moving gas. Now, let us see that when this gas does not see the sound wave, its conditions are defined as pressure P, density rho, and the other side of this, the corresponding parameter on the other side would be P plus dP, because it is a very weakest disturbance, and density is also will change in this process, that is rho plus d rho. Okay. So, if I try to plot this an xt diagram, where x stands for the distance along this piston and t stands for time, that means we are looking at this wave at different time instants. At one time instance, when the wave is at this location, I draw a line So, let us see that what happens. So, first thing is says that this line denotes the motion of piston. So, we call this as piston path. So, because this dV comes from this xt diagram through this piston path, and the movement of this wave we can represent in this manner. So, we call this as pressure path of pressure wave. So, this is how we see in xt diagram. Similarly, on pressure and distance diagram, one can see that one side of the piston, that is a pressure P plus dP, but just at this vicinity of this moving gas, pressure again comes down to original pressure of the stagnant gas P. Now, same thing when you draw this velocity versus x diagram. So, we can say that initially this piston has this velocity, and all of a sudden this velocity drops to 0. So, this value is, we say dV, this magnitude is dP. So, this is how we do in a moving frame of analysis. So, it means that I am looking at the wave sitting in the laboratory. Now, let us see that I want to bring a stationary frame of analysis, where the gas stationary gas analysis, where we say we bring this wave to be stationary. So, this is this all these plots in this side is the analysis for stationary wave. We see that the wave is treated to be stationary. Now, to address this, how I bring the wave to be stationary? So, effectively, so when I say this wave to be stationary, I have to artificially initiate a flow that that changes similar properties. So, in the beginning stage we say same pressure and density, and we say this to be a very thin region across which the property changes, and this velocity in one side the pressure is P, density is rho and velocity is A, and in other side we say the pressure will be P plus dP, density will be rho plus d rho. Now, if we say this wave to be stationary, then obviously I should get a velocity A minus dV for the other side of the gas. So, this is your stagnant situation, this is your of course, this side also flow is stagnant. The conditions at one particular time instance, the condition will be P plus dP, rho plus d rho. So, I should subtract a minus dV because the piston movement is originally in these directions. So, the speed that happens will be A and A minus dV. So, likewise one can draw from this particular point, that means here we have to draw with this wave as the starting point. So, from there I can draw this piston path, I can also draw the moving fluid. And path of wave. The pressure plot will remain same as it is, and but velocity will be something different. So, we have to bring a reference line which is much below this, because the directions are opposite, where you say it is minus a minus dB, and from there it will start, finally it will end with a, because directions are taken in the opposite directions when you look at in this frame of reference. So, I hope I make you understand about this concept, and in the subsequent analysis we will now recall only this particular figure which will come into our equation. So, whatever I told, I will just brief about it. Say in moving gas analysis and stationary gas analysis, what we looked at, an infinitesimal disturbance created by the piston induces a compression wave that moves at speed of sound into the stationary gas. Now, at one particular instant of time, the piston attains a steady velocity and becomes equilibrium. So, when it happens, the pressure and density next to the piston face are infinitesimally greater than that of wave. That means, there is a slight increase in the pressure and density. So, in this process we can make a dynamic transformation when the motion of the wave can be studied by keeping wave to be stationary. Now, to do that, we have to create to do the mathematical treatment, we have to create a differential control volume across which the basic equation of motions can be addressed through one dimensional framework. Now, let us see how we are going to address. So, first thing we are going to address the continuity equations. So, obviously, when you talk about the continuity equations, the parameters of interest we have to say is, say this is how you have this control volume. So, here the parameters of interest are A, rho in one side, and that changes is A minus dV, and in other side of the wave we have A minus dV and rho minus rho plus d rho, and this thin region of control volume we are going to see that, and medium is one dimensional. We assume that there is no mass or there is no heat and there is no work interaction. Having said this, the first equation that is going to be written is the continuity equations. So, we can write m dot is equal to rho A that is equal to P rho plus d rho into A minus dV, and we are saying this entire area to be A on both sides of the wave. So, if you simplify these equations, what we are going to get is that you get a term d rho dV which can be neglected, and this rho A, rho small a and capital A will get cancelled, and finally, what we get is rho A dV will be equal to A d rho, and the end expression is which you are going to get is dV is equal to A by rho into d rho. So, this is nothing but this equation. So, this is the equation which we get from the continuity equations. Moving back to the momentum equations, here the parameter of interest will be P and A, here will be a P plus dP A minus dV. So, the momentum equations can be written as by considering the Newton's law for this one dimensional medium. So, we say P plus dP minus P into A will be equal to m dot A, that is rate of change of momentum, into m dot A minus dV. So, one can simplify these equations. Also one can write m dot is equal to rho A and A, which is we get from the continuity equations. Now, after expanding these equations, we will get cancelled so many terms, there will be a term A. So, that term that is going to cancelled is P A will get cancelled, m dot A and m dot A will get cancelled. So, ultimately what we get dV is equal to A dP divided by m dot, that is nothing but A dP by rho A and A. So, A gets cancelled, we say dV is equal to 1 by rho A into dP. So, this is what we get from these momentum equations. Now, moving further, when you talk about energy equations, here I like to emphasize there is no work interaction, no mass interaction, there is no work interaction, there is no heat interactions. The parameters of interest are H plus dH and H, and where velocities are A and A minus dV. And one thing we need to emphasize, that we do not consider the elevation, that is what we say the change in the elevation is negligible, there is no change in the elevation. So, for that potential energy term will not come into account. So, for this reason we can write this energy equation beginning as H plus dH plus A minus dV whole square by 2, that is H, that is one side of the piston, one side of the gas, other side will be H plus A square by 2. And this equation can be simplified, that is H plus dH plus A square by 2 plus dV square by 2 plus 2A dV by 2, that is equal to H plus A square by 2. So, this will get cancelled, H will get cancelled, and finally simplifying we get dH will be A dV, here it will be minus, this 2 will get cancelled, this term tends to be negligible, we can neglect this term, and finally we arrive at this relation. So, having said this, we say that this we will now revisit the entropy equations. To recall this entropy equation, first thing what you see is that we recall this TdS relation. TdS is equal to dH minus dP. One of the TdS relation says that TdS is equal to dH minus dP by rho. Now, for this particular problem, from the energy equation we get dH is equal to A dV, and from momentum equation we get dP by rho is also equal to A dV. So, obviously, when you put this equation we say TdS is equal to 0, which means ds is equal to 0. So, this gives a very important inference what says that entropy change for the whatever problem we say is there is no entropy change. Hence, we say that when a weakest disturbance is created in the medium through a sound wave, the entire process can be treated to be isentropic. So, that is the emphasis what we are going to get from this analysis. Now, we will again see that when we say that this process is isotropic process, then we will see that what speed the wave moves. So, when this particular speed, we call this as a speed of sound, or many books also talk about this as a acoustic speed. Almost both are of same nature. So, but most routinely used term is, we say it is a speed of sound. Now, let us derive the speed of sound, which is a, we can relate this to term as square root of gamma p by rho, or we say that A is equal to square root of gamma r t. Now, to do this, what we have to recall now from continuity, we get from the continuity analysis, we get d v is equal to A by rho d rho, and from momentum equation we also get d v, but in terms of pressure, d v is equal to 1 by rho A into d p. So, when we equate these two equation, what we get, A by rho d rho is equal to 1 by rho A into d p. Then we can get a term as A square as d p by d rho, and we also proved that although it is a differential equations. So, we also proved that when we define the speed of sound, the process happens to be isentropic. So, these differential equations, a more appropriate way of representation would be in representing in a partial differential equation d p by d rho for constant isentropic process. Now, let us evaluate what is this d p by d rho. So, for an isentropic process, we say P is equal to 1 by P by rho to the power gamma is equal to constants. Now, this equation we can write in terms of logarithmic, that is ln p minus gamma ln rho is equal to constant, some other constant. Now, you differentiate, we say dp by rho minus gamma d rho by rho is to be 0. So, this becomes, when we represent in terms of isentropic way, from this dp by d rho, from this expression we can find out is gamma p by rho. So, thus this A square becomes gamma p by rho. So, this is how we get for an isentropic process. We say that square of speed of sound is function of pressure and density. Next thing comes that for this equation can be further simplified by recalling equation of state. So, we say equation of state P is equal to rho r t. So, from this equation we can find P by rho to be r t. So, when I say this, and we can put it here, and finally, we land up with these important expressions, speed of sound in two forms. One is square root of gamma p by rho, and other is square root of gamma r t. And under atmospheric conditions, when you put gamma to be air, gamma for air, and temperature to be 298 Kelvin, 25 degree centigrade, then this we can evaluate the speed of sound. And in most appropriate term we say the speed of sound is the order of around 340 meter per second under normal circumstances. Now, we will move further to define another properties, that is called Mach number. So, when I define the speed of sound, that is the disturbance that moves in a medium, but why that disturbance moves, but at the same time we say that your body is moving with certain velocity. That means, your moving gas also has certain velocity. So, considering that when there is a relative velocity between the body and the compressible fluid, the variation of density influences the properties in the fluid. So, for which we define a non-dimensional number known as Mach number that relates the velocity of the body to the velocity of the sound. So, m is equal to v by a. Interestingly, this Mach number relates the direct measure of the directed motion. This directed motion is nothing but your that relates to the kinetic energy v square by 2, and also to the random thermal motion. So, this random thermal motion is with respect to internal energy. So, interestingly, one can find out that ratio v square by 2, that is the kinetic energy to the internal energy. If you can calculate or simplify based on for a common calculations, this ratio happens to be gamma into gamma minus 1 by 2 into m square. So, essentially what I am trying to say here is that the ratio of kinetic energy to the ratio of internal energy is a function of Mach number. So, one can say the Mach number is also an indirect measure. Now, moving further, what we see in this for the gases, we say that the gases normally behave as a dual nature. Dual nature means under some situations gases behave as a incompressible medium, or gases can be considered as a compressible medium. So, what is that? Circumstances. So, that essentially we see that this all depends on the pressure and velocity. That means, if the gas is moving at low velocity, it may be treated as a incompressible medium because the pressure changes is small, but if the gas moves very high velocity, the pressure changes are very significant. One cannot assume to be a incompressible medium. So, for which we define this Mach number as a limiting case. So, a non-dimensional number that comes into picture is the Mach number, which is the ratio of v by a, and it has been shown that if the Mach number is greater than 0.3, so we can say the compressibility effect is predominant in the medium. So, based on this, the all high speed flows are decided in terms of Mach number. When the Mach number is less than 1, it is a subsonic flow. When the Mach number is equal to 1, it is a sonic flow. When Mach number is greater than 1, it is a supersonic flow. We will discuss about in this course in the subsequent lectures, but the most important point to be addressed here is that under what circumstances the compressibility effect comes into picture. And this condition turns out to be fact that for this condition Mach number, your velocity is the hardly in the range of 100 meter per second. That means, when your body is moving at more than 100 meter per second, we expect a change in the density, that is d rho by d rho is to be higher than 5%. So, this is how the standard typical definition, normal layman sense one can give, that when the density changes are higher more than 5%, the medium can be treated to be incompressible. Now, moving further, we will now move on to the next topic, that is isentropic flow. Since we say the medium to be isentropic when there is a disturbance occurs. So, based on the isentropic flow, we will now define some properties which is known as stagnation properties. and for to define the stagnation conditions, to define the stagnation conditions in a compressible medium, we say that these are kind of a hypothetical properties. So, before I explain further, just to give some insight that an isentropic process provides a standard, gives a useful standard for comparing various flow conditions with respect to an idealized flow. And this isentropic process, we call this as to be reversible and adiabatic process. So, when you say the process to be reversible adiabatic flow, and we get this information from the second law. So, considering this as one of the important consequence of the second law, in our compressible flow situations, we defined some states which is called as stagnation states. So, the stagnation state is a state where the fluid is treated to be a reservoir. So, fluid happens to be in a state where it is as if it is lying in a reservoir, but there is a thermodynamic meaning to this state. So, we will now give some these thermodynamic meanings to this state as a stagnation state for the fluid. That means, any fluid might be moving, but it will have a hypothetical state which is known as stagnation state. How this hypothetical state will achieve? When the fluid is isentropically slowed down to 0 velocity. So, this is how the thermodynamic definition of a stagnation state is all about. So, the fluid can be accelerated isentropically to axial states from a thermodynamic stagnation state having 0 speed. This is another angle one can interpret, that one can accelerate a fluid from a stagnation state. Either a moving fluid can be brought to rest, or a flowing fluid or a stagnant fluid can move to a active state. To define these things, what I am trying to say here, that we now say that as if we have a reservoir having certain conditions of pressure P naught, temperature T naught, density rho naught, these are the properties. Okay. So, to study the stagnation conditions, we define these things in a standard way as P naught, T naught and rho naught, but it happens to be at 0 velocity. Now, we want to create a flow from this reservoir. So, we say it is a reservoir. So, one can imagine that this fluid is at very high pressure, high temperature and density, such that it can induce a flow to happen in certain passage. So, we are allowing this flow to happen in one of the passage by creating a hole into this reservoir, and we allow it to go to a stage. So, this is how we define this your active state. That means, P or rho, T, all these parameters we say as a active state. So, active state means as if this flow gets generated from this reservoir. So, hypothetically what it says is that the fluid can accelerate from reservoir to arbitrary state, or fluid can decelerate from its active state to the stagnation state. So, this is, if this is your initial stage, one can accelerate this fluid to final state. We can accelerate the fluid, and this process is isentropic. Other angle D state, if we assume this to be an initial state and we come to the final state. So, here you have to decelerate the fluid and the process is also isentropic. So, in other words, what we are saying, any arbitrary fluid state has a thermodynamic situation which is known to be a stagnation state, and that condition is reached through an isentropic process. And the corresponding notations what we give, we for pressure arbitrary state is denoted as P, corresponding stagnation state is denoted as a P subscript O or P subscript 0 P naught. Similarly, T, T naught, rho and rho naught. This is how we view this. Now, let us see that how it means to us in terms of a fundamental diagram which we normally represent for an isentropic flow, what we call as Mollier diagram. This Mollier diagram has x axis as entropy and y axis as enthalpy. And on this Mollier diagram, thermodynamically one can represent constant pressure lines. So, these constant pressure lines for our case we can say, because in our case our two constant pressure lines, one is P, other is P naught. So, obviously stagnation state will have higher pressure, so it is denoted as a P naught, and what we say is that when we are going from either static state to stagnation state or from stagnation state to static state. So, in this case we get the first case, we get either you can come this way or you can go this way. So, on this process we say entropy remains constant. So, for this process one can also draw the temperature entropy diagram. Here the curves will be little bit steeper. This is also S is equal to S0, and the temperature terms we can say T naught line, this is T line. So, this is how one can say we call this as a static temperature and we call this as a stagnation temperature. Here we call it as a static enthalpy and here we call it as a stagnation enthalpy. This is how the concept behind the static temperature, static pressure and static enthalpy. So, whatever I told, if we want to just summarize, what we can say that the associated fluid parameters of the fluid in a hypothetical stagnation state are called as stagnation properties. So, one can have stagnation pressure, stagnation temperature and stagnation density. The stagnation all the stagnation properties can be assigned to the fluid when it is actually moving with a finite velocity at certain conditions of pressure and temperatures. Many times the total properties are also used similar to stagnation properties. One other important inferences that we get from this stagnation enthalpy and stagnation temperature is that the term associated with velocity. For stagnation enthalpy we say V square by 2 and for stagnation temperature we say V square by Cp. What you see is a dynamic term. Okay. So, if I say stagnation enthalpy or stagnation temperature, implicitly this dynamic term is already taken into account. So, this is happen, this is how we do, this is how what is the advantage of talking about stagnation temperature or stagnation enthalpy or stagnation pressure in addition to its static value, because the velocity components are already incorporated in these equations. Just to moving further, whatever analysis we do, we did it for the last case. Now, we can just revisit that analysis just to say that just to analyze the energy equations in terms of stagnation temperatures. So, the first thing what we are going to study, that if the flow is steady for an adiabatic compression system, if the flow is steady without work transfer. In all our analysis, we never consider work transfer and heat transfer. Just to for the sake of work transfer and heat transfer, and we define the stagnation properties, how these equations we can address. So, for that we talk about a process which goes from 1 to 2. Now, when some system goes from 1 to 2, we can write the energy equations in this form. Now, in this equation, if both 1 and state and 2 states are at same elevations, we can neglect G Z1 minus Z2 to be 0, and all the analysis we consider for unit mass of the fluid, and when it goes from 1 to 2, the heat transfer and work transfer are related through these energy equations, that is Q minus W. Now, for the first case, when the flow is steady, but it is a adiabatic compression systems. So, we get Q to be 0, and this will turn out to be W is equal to, it is a compression system, Cp T naught 1 minus T naught 2, where T naught, where we say Cp T naught 1 is equal to H naught 1 and Cp T naught 2 is equal to H naught 2. And in other situation, the second case, when it is without work transfer, so we say W to be 0. So, the heat added H will be Cp times T naught 2 minus T naught 1. So, it is a added, sorry, this will be Q. Now, the last part of this topic is the isentropic relations, which is a very commonly written as for an isentropic process, where P by rho to the power gamma is equal to constant. So, for that process, a commonly used relations we can write P naught by P is equal to T naught by T to the power gamma minus 1 by gamma minus 1, that is equal to rho naught by rho to the power gamma. So, here your the thermodynamic process which goes from 1 to 2, here we consider 1 as arbitrary state, 2 as stagnation state. So, when you say arbitrary state, we say P, T and rho, and when you say stagnation state, we say P naught, T naught and rho naught. So, by recalling this ds to be 0 and this equation as this, entropy equation as this, one can derive from these relations, one can find out these relations with respect to ds by 0, and using these equations one can write, and also we have to use the relations like Cp by R to be gamma by gamma minus 1, and we say Cv by R 1 by gamma minus 1. and once we simplify the entropy equations, we can frame these most important relations what we call as the static versus stagnation relation. So, with this I conclude for this lecture for the today. Thank you.